Today's modern ag planes have come a long way since the early days of underpowered aircraft that could barely take off, let alone fly with a full load. Greatly improved structural designs and higher performance, more dependable engines give today's ag aircraft significantly improved crashworthiness and an increased margin of safety for the pilot. But an ag airplane, like any aircraft, is only as safe as the pilot who flies it. Flying with an improper attitude, making poor decisions, and pushing the plane past its safety envelope can lead to serious accidents and, in many cases, fatalities. Getting in the habit of making turns that are too quick or too tight increases your risk of a stall, which can lead to loss of control, an extremely serious situation in ag work since there's rarely sufficient altitude to recover. Over the past 10 years, more than 200 ag aircraft crashes have been attributed to loss of control. In fact, loss of control during a turn is one of the leading causes of fatalities in ag flying accidents. The purpose of Turn Smart is to provide information about how and why these stall situations can occur and how to respond if you find yourself in this type of situation. Veteran ag pilot and aerobatic performer Wayne Hanley, flying his aerobatic plane the Raven and a turbine air tractor AT-502B, will explain and demonstrate various maneuvers that can result in a stall, along with helpful advice on how to recover if you find yourself in this situation. Wayne will also cover the importance of not pushing your ag plane beyond its safety envelope. Most importantly, however, Turn Smart is designed to show you that with the productivity of today's modern aircraft, there is simply no need to make high-risk turns. There is very little to be gained and very much to be lost.
Hello, I'm Wayne Hanley. I had the pleasure of being in the ag aviation business for 25 years and still maintain my affiliation with both the California Ag Association and the NAAA. Since selling my ag business, I've gone into air show flying and do a little aerobatic instruction in the wintertime. The big differences I see it between ag flying, one of the big differences between ag flying and aerobatic flying is in an ag flying, we're flirting. We're just testing the edge of the flight envelope out in the deep part of the turn. In aerobatic flying, we are intentionally, and I emphasize intentionally, we're going outside the envelope. With an aerobatic airplane, we intentionally go out, we have the safety net of altitude, and we have an airplane designed to do that with a very high roll rate. When we're flirting with an ag airplane, we don't have the safety net, we don't have the roll rate, and it can be very dangerous. Sadly to say, we're still losing several people every year and aircraft in these out-of-control situations. It can happen to the high-time pilots as well as the low-time pilots, and we're seeing that as a result probably of the development of some bad habits. And you've got a bad habit working with you, and you get a surprise such as an engine failure, possibly an in-flight sulfur fire, or you hit the wake from another airplane you're working with, and you can get a real nasty surprise. Let's take a look at a couple of uncoordinated turns where I intentionally take the airplane past the maximum angle of attack. I feel it's imperative that you accurately anticipate the control response if you do go outside the envelope.
I will establish a steep turn to the left. I will use top rudder to slip the airplane. And when the airplane stalls, which way will it roll? We will do a skidding turn to the right. Which wing will stall first? Which way will we roll?
If you had to think twice about which way the aircraft was going to roll in each one of those stalls, I'd like to take you along for the rest of the ride.
And when the airplane stalls, which way will it roll? Over the top, and down we go. Which wing will stall first? Which way will we roll? Right wing stalls. We roll to the right. Takes left rudder, our top rudder. Relax the back stick, and we're in good shape again.
Let's use this model to illustrate the dynamics of a basic turn. Turning to the left, if we slip the airplane, the ball's going to go out to the left. The right wing is retreated, decreasing the airflow or the relative wind over the wing. We've had to cross control. We have right rudder, now we use left stick, lowering our right aileron, which in effect increases our angle of attack. This wing will stall first. we're going to roll over the top and down we go. Let's come back now to the left turn and we skid the airplane. Ball goes out to the right. Left wing retreats, decreasing the relative wind flowing over the left wing. We have to cross control. We're using left rudder, right stick. Now we have lowered our left aileron, effectively increasing the angle of attack. So this wing, the inboard wing, will stall. In a skid, the airplane's going to snap underneath and down we go. Okay. In the flight demonstrations you've just seen, I had altitude. I intentionally stalled the airplane, correctly anticipating which way the airplane would roll, and came in immediately with the correct control inputs. Now, if you're down in a working environment at turn altitude and you stall this airplane and do not come in immediately with the correct response, the airplane will continue to roll and could very well impact the ground. You may think that standing on the bottom rudder will give you the tightest turn. Wrong. If you're standing on a rudder, you're compensating with stick. So what do you have? Aileron down, aileron up, rudder off to the side. Very inefficient way to fly an airplane. Very dangerous way to fly the airplane. If you stall in this situation, it's going to go underneath. You've got to catch it with opposite rudder immediately. The instinctive thing to do is pick up that wing with the stick. When it drops, you want to pick it up. Don't do that. That lowers your aileron, increases the angle of attack on this wing, making it virtually impossible to roll the airplane back up. It's the misuse of rudder, not the stall, that causes the spin. If I was making a coordinated turn and exceeded my maximum angle of attack and I get into the buffet, all I do, obviously, is release the back pressure, decrease my angle of attack, and I'm flying again. But if I'm skidding the airplane, the skid will mask the buffet to a degree, and when that wing stalls, we go underneath. The corrective technique now is to step on the ball. As we've skidded the airplane, the ball goes out to the right. We step on the ball, opposite the direction of the rotation and the yaw. When we step on the right rudder, we swing the left wing forward, increasing the airflow, and we get the airplane flying again. When we skid the airplane and snap it out of a skid, it's very similar to the aerobatic maneuver called a snap roll. To show the correlation between a snap roll and a skidded turn stall, I'm going to come in with right rudder, slide the ball way out, snap it, around we go, back to level. So you can see a snap roll and a skidded turn stall have the same results. I'm going to skid the ball, skid to the right, ball's out to the left, stall the airplane, around we go, back to level. To further reinforce the importance of rudder work, I'd like to demonstrate a falling leaf maneuver. We stall the airplane in straight and level flight, and as the nose drops and one wing drops, we catch it with opposite rudder. As the left wing drops, I catch it with right rudder. As the right wing drops, I catch it with left rudder, and we walk the airplane down using the rudder. And the important thing here is, if we do not allow the airplane to turn, it cannot spin.
We're setting up for the falling leaf maneuver. I backed idle. I'm going to stall the airplane, continue to bring the nose up, holding this altitude. When the airplane stalls, I'm going to hold the stick straight back, and we're going to walk it down with rudder. The left wing drops, I come in with right rudder. There's the right wings down, I catch it with left rudder, right rudder. We use the rudder against the roll and the yaw. Left rudder, right rudder, relax the back pressure, and we're out. Just like in the snap underneath out of a skid or the snap over the top, if you use the opposite rudder from the roll in the direction of yaw and release your back pressure, you're back in good shape. And the sidebar on the falling leaf, if you do not allow the airplane to turn, it cannot spin.
Now let's discuss some of the problems and techniques associated with the higher risk turns, such as your high trajectory wingovers or hammerhead turns.
Okay, I'm at 2,900 feet, pulling power. I'm going to hold the altitude here and check the 1G level flight idle stall speed. There it is at 65.
Now that we've established that the aircraft will stall at 65 miles an hour under these conditions, I'd like to demonstrate a technique to be used if you came unhooked in the top of a high turn. Simply go to 0G. Decrease your angle of attack, 0G, A wing will not stall at 0 G. If it's not working, if you're not asking anything of the wing, it will not stall.
Here we go, just to show that at 0 G, the airplane will not stall. Bringing it up from 115. There we are at stall speed, 40, 30, over the top at 0 G, nose down, speed's back, G's back, I can pull out.
If you find yourself in trouble at the top of one of these high turns, resist that temptation to hold it in the buffet. Get that airplane to 0 G. Be patient. Gain as much speed as you can. Let gravity work for you. Use full throttle. The more speed you can acquire on the way down, the more G you have available to affect your pullout.
We were going to do a hammerhead type turn. We pulled up out of the field to the right, reversed back over to the left, dropped some flaps. If it unhooked right here, we don't want to come in with any more back pressure. Relax the back pressure, let gravity work for us, get some speed, and then we can affect the pullout. Speed is life.
Let's talk about a little common sense as it pertains to turn time. Just as an example, and not as a standard, I want to use the 30-second turn because it's easy math for me. If we had a morning where we made 100 turns and we were averaging 30 seconds and we were right on the edge through these 30-second turns, then we backed it off 10%. Now our turn time is 33 seconds. We're much deeper in the envelope, we're much more comfortable, and we're much safer in the event of an emergency of any kind. Okay, we've increased 3 seconds over these 100 turns. We now have 300 seconds added to our day's work. 5 minutes. 5 minutes is all that amounts to. And it's so easy to regain 5 minutes in your operation elsewhere. I'll back it off 10%, be a little deeper in the envelope, and probably be a little less tired at the end of the day. We've just covered a lot of information and looked at a couple of techniques on how to get out of trouble. But the bottom line is that today's ag aircraft are so productive, there's just no justification for jeopardizing your safety or your equipment on these high-risk turns.